morning, everybody. Thanks for sticking it out for the end of the first session. I'm really excited to be here. Thanks, Paul, and the organizers for having us. I hope that this will tie up a bunch of the themes that you've heard already today between partnerships and corn and ethanol, as well as low carbon solutions, and most recently, I think we heard about trying to be cost competitive with petrochemical processes, because that's the thing that actually drives the broad adoption, and we need to find a way to get there. So as the 15-person startup in this group, we're not 100 years old, we're just about a decade old, but I'd like to encourage everybody one more time to just sort of think big here. Like, what is it that we want ultimately? What's the big dream? We're trying to get to something that is cost competitive, zero emissions, bio-based, and how do we get there? And so that's sort of where we started with this project, thinking like there are all sorts of products around us in our everyday lives. We don't even notice probably where they come from. And most of those products are coming from petrochemicals, mainly because we can't get them cost competitively today from a bio-based solution. Everybody in this room would buy something that was more sustainable if it cost the same or less. So of course, here in Nebraska, talking about corn and ethanol, we've used it for centuries for food and for feeding our animals. More recently, we've been using it as a fuel. And at Industrial Microbes, we're looking at using that as a feedstock for making chemicals. This is a great way to take CO2. It's like direct air capture, but the easy way. You're getting that put into plants and brought efficiently into products. And of course, if we can efficiently turn that into chemicals and materials, then we can have carbon negative or net zero materials. Ethanol is a particularly fantastic feedstock for a bunch of different reasons I have here, but the ones I'd like to point out, similar to what Doug was saying, here in the US, we have this incredible infrastructure to support the production of ethanol. What I think is particularly exciting about it is it's not just a cost-effective solution for today, but it's also something that going into the future, it can be a transition. And I think we need to be thinking long-term about how do we get to a fully circular economy. And part of the way to do that is to set up technologies today that can help us in that smooth transition. And we're already seeing many different strategies today about how to get to ethanol in the future that might be more efficient or from more waste sources beyond just using our land to grow plants. We can also imagine using municipal solid waste or even possibly someday direct CO2 electroreduction. So at Industrial Microbes, what we've been building is a microbial platform that can convert ethanol into a variety of different chemicals. We've engineered, starting with E. coli, to be able to do that. And our first product will be bio-based acrylic acid. It's used to make all sorts of different products, such as the superabsorbent polymer in diapers. It's an ingredient in paints and coatings and adhesives and cosmetics and a whole bunch of other things. A very versatile product, which is one of the reasons why we've been interested in it. And when we've spoken to people in the industry closer to the consumer, they've been really interested in trying to get this product. And there haven't been a lot of strategies out there. Right now, today, it is produced using a mass balance approach, but it's about twice the cost, and that's been hampering widespread adoption. So we've developed a process that involves taking an engineered microorganism, doing a fermentation where we end up with a polymer that actually accumulates inside the cell. It's called poly-3HP. And then we can go through a very simple downstream process where we raise the temperature to a pretty moderate level, and it thermally decomposes into acrylic acid, which can be separated to very high purity just using distillation. So trying to focus on cost, what we're thinking about is, of course, the feedstock cost, but also simplifying the process to take out as many unit operations as we can and make that as efficient and cost-effective as possible. I think this is kind of amazing, but actually E. coli, the strain that we're using, can accumulate this polymer, poly-3HP, to more than 90% of its weight. So just imagine like becoming suddenly 10 times your normal mass because you've been filled up 90% with this inert polymer. But it's actually a very effective strategy. In our lab, we've already been well over 80%, and we know that other folks have gotten above 90, and it's really critical to make the economics and the efficiency of the downstream process work. So by doing that, we've done a detailed techno-economic model with a couple of experienced bioprocess engineers in the space to try to understand what does the cost structure look like and how cost competitive can we really be. And what we found was we can actually, when we get to the commercial target metrics for our process, we'll be able to produce acrylic acid actually at about 20% lower cost than the typical process today, which is derived from propylene. We've gone through this in quite a bit of detail. If we do that, compared it to the average price of acrylic acid over the last several years in the US, we'll actually be about doubling the profit margins in this product. And that's not including any assumptions about the government support or carbon credits, and it's including all of the cost of building the capital from scratch. More recently, we have made significant technical advances in our lab, and we've seen that the projected cost of our product is coming down very, very rapidly, because as you increase the yield, productivity, and titer of your fermentation process, your cost per ton of production goes down actually quite rapidly. We set up technical metrics that we aim to hit by the end of next year, and we are well ahead of schedule. So I think that this is a process where our organism is just really happy to go through with that. Shifting to talk about the carbon footprint, using our techno-economic model, we can make an estimate of what the carbon footprint will be when we scale this up. And we have seen at least 75% projected reductions in carbon footprint. The typical process emits about 3 tons of CO2 equivalent per ton of product produced. Using corn ethanol today, the average corn ethanol in the United States would immediately reduce carbon footprint by about 75%. And then more advanced, lower CI score sources of ethanol, many of them listed here, would allow you to get further and further down. And so getting ultimately to a negative CI score. And so you can actually imagine balancing the feedstock that you put into this in order to end up with a net zero product and get the advantage of cost and net zero product at the same time. So most recently, we've had a bunch of exciting news. In June of this year, we did our first scale-up run supported by the Department of Energy's Agile Biofoundry and the ABPDU in California. We scaled up to our first 300-liter scale fermentation run. We saw fermentation metrics that exactly matched what we were seeing at the 2-liter scale, so a very successful run. We produced our first 2 kilograms of polymer that's in processing right now for purification and conversion to acrylic acid. And then in August, with support from BioMade, thank you very much, and here in the Midwest in Illinois at IBRL, we scaled up even further to 1,500-liter fermentation volume. And again, we saw very predictable results, producing over 10 kilograms of product that we're going to be starting to do application testing on this fall. And in August, we just also began a project supported by DoD, the DBIMP program, to help us plan our first commercial facility. We kicked that off a few weeks ago. It's going to allow us to do all the FEL2 engineering design for our first commercial plant, and that'll allow us to move to the next stage of planning for commercialization. And the reason that we're here is to talk to everybody in this room about how we can work together to advance these kinds of solutions, and especially here in the Midwest, where we would like to plan that first commercial facility to integrate as closely as possible and co-locate ideally with ethanol production in this area. So we're very interested in learning more about that. We think that by combining forces, by co-locating, we'll be able to further reduce the costs that we put into our model, process integration, utilities and heat integration and so forth. And we think that that will significantly advance this project. So if you're in the ethanol industry, if this sounds interesting to you, please come find me. I have a booth right outside at the end of the hallway here, and I'd love to talk to you. So thanks very much.